Whether in forensic science for investigation of criminal activities, in money printing, or in the development of modern X-ray images, luminescence is used everywhere, but also when it comes to the behavior of radioactive substances in the environment, and in some homes it is used. We should clarify exactly what luminescence is, as today we'll be looking at laser-induced fluorescence spectroscopy, LFS, and later at TRLFS of the elements Europium and Curium, and comparing their fluorescence with the uranium fluorescence. As always, this will be very advanced stuff, but we'll get there. I will use this content to discuss the fluorescence of uranium glass again in a separate video. So you can think of this as being a bit of a deep dive into fluorescence. So let's break down the intro. This is a recording of luminol, a fluorescent substance reacting with oxygen. In other words, it's a chemical reaction that produces light as a result. Okay, so apparently it has something to do with light. Ultimately, the term luminescence is basically a safe space like the term particle in chemistry. Very general and in case of doubt, not wrong at first glance. But unfortunately, also not particularly precise. Luminescence describes any case in which a system has energy and then emits at least some of this excess energy in the form of light. In this example, the system was a chemical system excited by a chemical reaction. So we are talking about chemiluminescence here. In the case of the banknote, this is not a chemical reaction that I used to excite the system, but rather I shone a kind of light on it. Okay, not in the visible range, but they were photons. Accordingly, this is an example of photoluminescence. And the developing part of X-ray images is also photoluminescence. There are many other types of luminescence. Bioluminescence is actually just chemiluminescence, but it's a chemical reaction in biological organisms, hence bioluminescence. Okay, now I've talked about the excitation. In the following part of the video, we will only have photoluminescence. And now we need to differentiate how long this excited state lasts. This is how we distinguish between fluorescence and phosphorescence. Roughly summarized, fluorescent is short-lived, phosphorescent is long-lived. There are historical reasons for this naming. For the sake of completeness, I will summarize this very roughly. What is always excited are electrons, and electrons have spin. In an excited state, they can end up with a certain spin. Depending on this spin, it is easy to fall back into the ground state and thus also emit light. So quantum mechanically it's allowed and then it happens quite quickly, and in other cases, this transition is quantum mechanically forbidden. Forbidden meaning that such a transition just takes a lot of time. And thus the emission of light after the original excitation occurs with a significant time delay. The later would then be called phosphorescence. This was just an aside. We'll stick to photoluminescence and specifically photofluorescence. So much for the physics background, but what does it have to do with radioactive elements in the environment? Let's take the example Chernobyl. In a nuclear power plant like this, new radioactive elements are produced during operation through nuclear reactions, including the all-important nuclear fission. These new elements include fission products and transuranic elements. To put it simply, our reactor runs on 3 to 5% enriched uranium. The enormous neutron flux during the reactor operation can also give rise to new, heavier elements, in significant quantities up to curium. But theoretically up to fermium, only the quantity decreases the further we move away from the starting material uranium. In practice, a normal nuclear power plant can reach up to curium 245 or 246. In this case, we are talking about the other 95% uranium 238. Chernobyl exploded and released radioactive elements. These included the early lanthanides as fission products and the minor actinides as activation and decay products, as well as the fuel itself. Now we refer to the decay products as minor actinides and those after uranium as transuranic elements. In the term of reactor operation, the term minor actinides typically refers to the first 8 actinides contained in an average nuclear power plant after burnup, with the exception of uranium and plutonium, which are major components rather than minor ones. Depending on the context, there are different names for this group of elements, some of which will overlap. Just wanted to point that out. Actinides in particular are really something else, as they are heavy metals that are also radioactive. If you look at europium, it is a very rewarding element. This is because A, it is available in a non-radioactive version, which cannot be said for the elements below it, and B, it is very similar to the element americium. There was a thought behind sorting these elements in the periodic table. In the case of americium, americium-241 is a very well-known and relevant isotope. It is incredibly toxic and is produced in significant quantities during nuclear power plant operation, and is also produced after the release through the decay of plutonium-241. Now in the form of europium, we have a harmless analog with which we can conduct research and which, like americium, exhibits photoluminescence. And with curium, well, we'll just take curium-248, since this one also exhibits a beautiful orange fluorescence. Here we have a dissolved protein from camel milk in a glass cuvette. In this case it's caseinate, on which sorption and complexation studies were carried out using non-radioactive europium. To be honest, I could have sold you this colorless solution as anything else I wanted to, but just take my word for it. This cuvette is placed in the spectroscope with a protective cap on to keep the temperature reasonably constant. Now the europium can be excited, or rather the electrons of the europium 3+ ion. The fluorescence can be elegantly controlled in a very targeted manner by exciting with exactly 394 nanometers, i.e. in the near UV range radiation. Here we have the fluorescence spectrum of the aqua ion. That is Europium 3+, surrounded only by water ligands. There are about 8 to 9 water ligands. Today we are only interested in somewhat dissolved ions, and you can see some peaks very clearly. How did this happen? Well, Europium 3+ has the electron configuration xenon 4f6, so it has occupied f orbitals. Energetically, the 5d level would be slightly above it, which in the ground state is only occupied from lutetium onwards. But we are exciting these electrons with a UV laser. This means that in an excited state, the electrons can also be present in the 5d level. In this case, the excitation was achieved by 394 nanometer UV. It also works with 465 nanometers, but then the electrons are excited only to a lower level. At 394 nanometers, you go from the 7f0 to the 5l6 level, and with 465 nanometers, you can go only to the 5d2 level. These are simply the names for these energy levels. What I am showing here are the energy level diagrams of Europium 3+ ions. From the 5l6 level, there is first a non-radiative transition into the 5d0 level. We cannot see this in the spectrum because it's non-radiative. And now there's either a transition to the 7f1 level with the emission of 594 nanometers, or to the 7f2 level with the emission of 617 nanometers, or to the 7f3 levels with an emission of 654 nanometers, or to the 7f4 level, which is associated with an emission of 702 nanometers. Over time they will all fall into the ground state, but this is no longer in the visible range. We therefore name these bands the f1, f2, f3 and f4 lines. Cool, but now what? Take a look at the spectrum from europium bound in casein for comparison. There are now two very dominant differences. With a new band, an F0 band, and the relative intensities of the F1 and F2 are reversed. Now the F2 is the more dominant one. This means that the chemical environment affects the fluorescence. Here I have two more beautiful spectra, as those on screen were just part of current research. From this difference we can now draw a conclusion about the complexation. Here, for example, we see the spectrum of a Europium 3+ dissolved in water, which is then surrounded by only 8 to 9 water ligands. So that's the aqua complex, and here's another complex. We can clearly see the exchange of the F2 and F1 band heights. What we have just looked at were essentially steady-state measurement, but it's not only the fluorescence color that changes as a result of the changed chemical environment, but also the lifetime changes both for europium and curium. Water quenches the fluorescence of both elements. This means that if you resolve the fluorescence over time, you can also use this formula to calculate, for example, the number of coordinating water ligands on that europium. We determined the half-life experimentally. The fewer water ligands, the longer the lifetime. This also applies to curium. A steady-state recording would look something like this, with a peak at 590 nanometer orange for the quasi-aqueous system. In other words, curium 3+ ions dissolved in water. The fluorescence can be shifted up to 640 nanometers depending on the chemical environment. Here too, the number of water ligands can also be calculated using a formula for time-resolved measurements over the lifetime of the fluorescence. Time-resolved laser-induced fluorescence spectroscopy is abbreviated as TRLFS. We now know how to investigate the chemical environment of europium and curium ions using laser-induced fluorescence or time-resolved laser-induced fluorescence spectroscopy. The relative height of these peaks shifts with changes in coordination. In addition, we get an F0 band when the complex is symmetrical. This can then be used to investigate speciation of europium as a proxy for the underlying americium. Americium and curium are simply just disgustingly toxic radionuclides that are produced in significant quantities in the reactor and could be released. So this measurement method offers so many incredible possibilities. Another radionuclide known for its fluorescence is uranium, or rather its highly mobile volatile and chemically stable form, the uranyl ion. Now let's take a look at the fluorescence of a uranyl compound, as this has also a wide range of application. Among other things, of course, uranium glass, but also uranyl chemicals such as uranyl nitrate hexahydrate from the laboratory fluoresce beautifully. Let's take a closer look at the uranyl ion. We can see that we have a bond order of 3 between the oxygen and the uranium atom. The uranium is in the oxidation state of +6 and thus formally has the noble gas configuration of radon. However, we now have such a highly charged ion that charge transfer occurs. This explains the yellow color of the uranyl ion. The uranyl ion is linear. Accordingly, we still have up to 6 coordination sites free around it. Here too, we have comparatively distant 5f orbitals whose energy levels can be strongly influenced by the surrounding ligands. First, let's take another look at the aqua complex. The fluorescent is again excited by a neodymium YAG laser. The actual wavelength is 532 nanometers, but frequency doubled. We then have 266 nanometers, again UV, which excites the fluorescence of the uranium atom. This is the sample holder for ambient temperatures, and there's even a sample holder for low temperatures, liquid nitrogen temperatures. For this purpose, the sample in the sealed cuvettes are simply stored in liquid nitrogen until measurement and then can be installed for measurement. After excitation, fluorescence occurs from a very high energy state. The fluorescent radiation is guided through fiber optic cables into the spectrograph, where it is broken down into its components so we can obtain a spectrum like this. We see lines from 470 nanometers all the way to 590 nanometers. We have 4 so-called uranyl fingers. These are not as fixed as those from Europium and Curium. Uranyl has 4 characteristic fluorescence bands, all of which are approximately 900 reciprocal centimeters apart. In contrast to Europium and Curium, uranyl does not exhibit a decrease and increase in intensity of energetically fixed bands, depending on the chemical environment, but rather a shift of all 4 fingers towards the red or the blue. In this case, we have a steady state absorption of uranyl which has been complexed by oxalic acid. Oxalic acid as a chelate ligand on itself offers many possible combinations for uranyl complexes, as you can see here, and each individual species has, among other things, shifted the uranyl fingers elsewhere in the spectrum. If, for example, the ligand is replaced by malic acid, this shift in fingers can also be seen very clearly. And as with Europium and Curium, time-resolved measurements can also be taken. Here too we can see a beautiful cascade of fluorescence spectra from which the lifetime tau can be determined. Different uranyl complexes also have different lifetimes. Here on screen you can see quite clearly how the bands shift in the time-resolved series of images. This indicates a uranyl species with bands further to the right in the spectrum, which dominates at the beginning, and another one with bands further to the left on the x-axis, which dominates later. This means that different parallel occurring uranyl complexes can be characterized in this way. So much for the time-resolved laser-induced fluorescence spectroscopy, and we will encounter this analytical method again when we take a look at the interaction of radionuclides with microorganisms. Among other things, TR-LFS can also be used for this purpose. A big thank you goes out to Dr. Robin Steutner, who showed and explained everything about this analytical method to me. Also to Max, who provided me with the spectra from his research. Link to the current paper will be in the video description, and to Professor Nina Huitinen, who made the video possible. Also thanks to Professor Dr. Stumpf, Head of Research Ecology Institute at the Helmholtz Center Dresden-Rossendorf, and of course to my Patreons for their financial support. With that being said, thank you for your attention and goodbye.